We're looking at the chapter 4, which will study matrices as a separate entities without attachment to any system of linear equations whatsoever. It turns out this is a good, matrices, they turned out to be very helpful. Matrices, they turned out to be very helpful in many applications. Some of you who will continue your study in engineering, in physics, in finance, you'll realize that many of the modern problems in all of these disciplines, you cannot approach them unless you know matrices. Just like recently, I just found very interesting applications in finance, for instance, but I can't show you this because we don't have time for that. Plus, it's not the objective of this course to get you impressed with matrices too much. Anyway, normally matrix, it's something which is like a table of numbers. We saw matrices before. I'll show you once the general look of any matrix, only once. It will be rather lengthy. You see, it's rather lengthy one. Normally, when you look at the matrix in general, you look at the table like this. We're not going to look at the matrix in general too often, so we're not going to write these huge tables too often. So I actually probably only once for the chapter, for the duration of chapter 4. So the table of numbers like this, and numbers may be real numbers or complex numbers, we call them a matrix. It has a size, so we have m rows, n columns, and that's the general look of it. A little bit more abbreviated way to write a matrix will be something like this. And this one I will use more often than this one because it's less to write. And basically it's self-explanatory. Again, it contains all of the information we need. It contains the symbol, which we use to denote the entry of a matrix. It contains the normally first index in your symbol. It represents the index for the row. And the second index represents the index for the column. And this one gives you the range for the index of the row from 1 to m for Mary. And k goes from 1 to n for Nicholas. So this kind of notation takes less space. I will use this from time to time, but even this one will be not so often as like some concrete choices of matrices. Sometimes you will see something like this, and the symbol which is here, it means that this one is a matrix, and the symbol like this, it represents the collection of all the space of all m times n matrices. So this symbol is just like a Rn. Remember, we had the Rn symbol, R with the superscript n, which stood for all of the n-dimensional vectors. This kind of symbol will represent all m times n matrices. So if you see something like this, or if you see something like this, it's a clear indication that this capital letter A represents an m times n matrix. So m times n matrix. When you have a writing like this, you see sometimes I will skip the specification of what happens with the indices because this writing is self-explanatory. The size of the matrix is here in this indexing. That's why here I didn't put what's the j, what's the range for the index j, what's the range for the index k. So every time from the context, if it is obvious what kind of sizing of a matrix we're looking at, in these notations I will not use that j and k specification. Yeah, so I have 3 examples of the matrix of matrices, like of a particular size, like this one. That's a typical matrix of 3 times 3 size. It says here, matrix of 3 times 3. You don't have to copy that. We will see this matrix a few times during this lecture. That's another example of, or maybe you have to copy that. Who knows? We'll find out in a second. It's another matrix of size 3 times 3, and I have another example of the matrix 3 times 2. Remember, it is a convention which we make with you today, is that first number here stands for the number of rows, second number here stands for the number of columns, and the same goes about the indexing here. First one represents the row index, the second one represents the column index. Typical matrices, and we will, in chapter 4, we will see what kind of operations you have to know about the matrices, because it's the standard things you have to be able to do with matrices. These are things which help solve lots of problems in application. Well, we'll start with the easy one, with the easy set of operations, which I call linear operations. These ones are very similar to those we do with vectors. These ones are the ones which are done in a per entry fashion. When you take entries and you do the operations on every entry individually. So 2 of them, it's like in this regard, matrices, they resemble vectors 100%. In fact, in the higher mathematics, there is no any distinction between matrices in this regard and vectors, in fact. So let's just look at the linear operations. Two of them exist, like with vectors. One of them is adding matrices, and the other one is scalar multiplication of matrices. So I have two of them here. Probably I'll keep it like this. So if you have two matrices like this, if I have two matrices of sizing, you see here's my sizing, m times n. Here's the entry symbol A, and here's the entry symbol B, two matrices A and B. I'll give you first the formal look of it. Sometimes you need a formal look of it, and I'll show you on the examples. But it's easy actually. So when you add two matrices, you basically add these two matrices entry by entry. So you take the JK entry, and that's the official reference to this A sub JK letter, JK entry, and you add with the JK entry of the B matrix, and you end up with the matrix of the same size. If you, for instance, if you want to scale your matrix with a number, like lambda, like with vectors, again, you do this in pure entry fashion. So you take every JK entry and you scale with this number, and that's the result of it. That's the result of it. There is a derivative of this operation, as usual. You can also subtract the matrices, which is not an independent operation. It's a derivative of the addition and scalar multiplication. But I keep putting this on the slides too. So if you subtract, you do the same thing. You just subtract your matrices to entry-wise. It doesn't say here, but of course lambda here is a real number. I'll give you I'll show you some examples here. For instance, I'll show you this example. For instance, if I take this A matrix, and if I want to compute the triple of that matrix, all I will do, I'll run across the entries of this matrix, across all of them, and I will triple every entry individually. And that's the result of that. 9, for instance, this entry is 9, triple of that is 27. This entry is -2, triple of that is -6. All of them here, one by one. If I add two matrices, again, if I add these two, A plus B, again, I just run through the entries of this matrix, A, and run through the entries of the matrix B, and I add them individually. And that's the result of it. Actually, I was thinking to do this kind of trick. If I take this square, is this 1, is 5, and here is 6 in a sum. Now if I do like this, look how beautifully we can demonstrate the addition of matrices. 1 plus 5 is 6. 2 plus 3 is 5. 3 plus 9 is 12. Yeah. That's crafty, isn't it? Yeah. Yeah. Thank you. I was hoping for some appreciation. Yes. Yeah. 9 and -2 together, 7. -2 and 4 is 2. Is a little bit off limit. 5 and -6. And well, I hope you get the idea. You do it in pure entry fashion, and you can move these boxes across the whole matrix and see how you do your addition. The same goes about the subtraction. I'll just open the result for you. I think you will be able to check this result without my help.